Mendel Nguyen, and he will be telling us about emergent, photons versus confinement, roles of vortices and monopole. Over to you, Mendel. It's green.
Oh, okay, great. Okay. Well, okay. Then I'd just like to start by thanking ICTS for their incredible hospitality, and thanks all for coming. This will be a talk about mechanisms of confinement, but more generally phases of theories which have an electric Zn one-form symmetry. And I'll explain what exactly that means as the talk goes on. So confinement, of course, has been an open problem for many decades. And for many of us, understanding confinement means to understand the mechanism. What are the dominant configurations in the path integral? I believe it's fair to say that today there are two prevailing competing pictures of confinement. The first I'll mention is magnetic monopoles. This is perhaps the most well-known one. The idea is that if magnetic monopoles condense, then you get a dual or magnetic version of superconductivity, and the vacuum becomes a dual superconductor causing electric flux to collimate. On the other hand, there is a different picture which seems to be more favored by those in the lattice community. And these are center vortices. And I suspect these are slightly less familiar. So I'll spend a bit of time reviewing what exactly this competing picture of confinement is. Essentially, they are configurations which have two-dimensional world sheets, and they're characterized by the fact that these world sheets can wrap a Wilson line, and that wrapping is accompanied by a Zn phase factor. So this is what I've depicted here, albeit in 3 dimensions. So the vortex is depicted as a one-dimensional object in space-time. This is due to lack of space. And you see that on the left, it's linking with the Wilson loop, and on the right, when you unlink it, you get this additional phase factor. Now, the basic idea of this confinement mechanism is that these vortices are very strongly proliferating, and they can wrap the Wilson loop, they can unwrap it, and you get all sorts of phase factors due to this proliferation. And this causes a highly destructive interference when you're computing the Wilson loop average, which gives rise to an area law. Center vortices are also... I believe they are different mechanisms, and I will argue that they are different. Yeah. So I will argue that they don't. But the idea is,
why did you think that they would?
So this one I will explain. They're deeply connected with a symmetry, which is very important, at least in the pure glue sector of Yang-Mills theory, of SUN gauge theory. This is called center symmetry. It exists in SUN gauge theory, at least when you have matter fields that don't see the center of the gauge group. Nowadays, it's called electric one-form symmetry. It's basically the prototype of what is called a higher form symmetry. I won't really use this language too much, however. The essential point is that Wilson loops are the order parameter for this symmetry. Under this symmetry, they transform simply by this Zn phase factor. And confinement, this symmetry, it is now agreed, is necessary to give a sharp definition of confinement. So confinement is the statement that the Wilson loop basically vanishes, has a vanishing expectation value. And this means that the Zn center symmetry is unbroken. And on the other hand, deconfinement is where the Wilson loop has a non-zero expectation value. And that's to say that Zn center symmetry is spontaneously broken. So in other words, the realization of center symmetry is what gives a sharp definition of confinement. And this is what I mean when I speak of theories with this symmetry. I will be talking about theories with, exclusively theories with this symmetry. So there's a analogy with domain walls, which is very important. And this idea goes back, I think, to the, you can find this idea back to in the early works of 't Hooft, when the slogan is that center vortices are center symmetry as domain walls are to discrete ordinary symmetries. So if an ordinary discrete symmetry is spontaneously broken, then you have domain walls, they're very heavy dynamical excitations. And similarly, when center symmetry is spontaneously broken, the signature of that are very heavy center vortices. Now, consider again the case of an ordinary discrete symmetry. And suppose you want to vary parameters such that you restore the symmetry. What happens? Well, this is a famous argument due to Peierls. You can understand the restoration of a spontaneously broken discrete symmetry as the proliferation of domain walls. In other words, you can view proliferation of domain walls as the mechanism of symmetry restoration. It's very tempting, therefore, to think of center vortices as something playing quite an analogous role. If you want to restore center symmetry, if it's spontaneously broken and then you want to restore it, hence getting confinement, you might think that that is signaled by the proliferation of center vortices, and hence center vortex proliferation can be viewed as the cause, the mechanism of confinement. But is that really true? So I'm going to spend quite a bit of time talking about Zn lattice gauge theory. I'll do this because this is the simplest context in which I can answer this question. And also, the Zn lattice gauge theory is essentially like the Ising model for this symmetry. It is the simplest possible model in which you can impose the symmetry principle. So I will talk about this in quite a bit of detail.
Center vortices, is there a picture of them in terms of think of them as a string?
I will get to how they're related, yes. Yes, they are indeed related. So this is the standard formulation of Zn lattice gauge theory. You have link variables A. They're quantized in units of 2 pi over n. This is the action. It's very simple. This is a Wilson type action. And it's very clear what is meant by a center vortex in this theory. Picture a 3-dimensional space-time lattice. So a center vortex has a 1-dimensional world line for simplicity. In this panel, you see that the world line of the center vortex is piercing plaquettes. And on each plaquette, you say that the phase, you say that the field strength is equal to 2 pi over n. So that is the meaning of a center vortex configuration in this lattice model. And in fact, practically any configuration of this lattice gauge theory can be viewed as a superposition of such center vortex configurations. This is a theory of center vortices.
Why is this flat?
Yes.
Think of it as 2 centers.
Yes, you can think of it like this. Yes. the middle picture. This is kind of a, it's a projection, I suppose, of this thing, yeah. Now, what are the phases of Z and lattice gauge theory? At very weak coupling, any non-trivial configuration of the gauge field is highly penalized. Basically, you're only allowed to have flat configurations. This is the Higgs phase, or topologically ordered phase. At very strong coupling, this is, of course, the confining phase. This is practically true of any lattice gauge theory. And naturally, this transition is decided by whether or not vortices proliferate. That is, there's some transition somewhere. This is a theory only of center vortices. That is the natural expectation. But actually, for n greater than or equal to 5, there is a Coulomb phase, by which I mean this is a phase with emergent massless photons. Use a famous phrase in physics. Who ordered that? This is a theory of just discrete variables. How is it possible that you can get a photon emerging in the spectrum? This is what we would like to understand. And in fact, when I said that the Z and lattice gauge theory was a theory only of center vortices, that was just a lie, because the vortices can meet at a junction. And this junction should be interpreted as a monopole. And these monopoles may or may not proliferate. This is space-time, yeah. Yes. Well, yeah, I'm thinking of Euclidean time, but yes, yes. Yes.
So you're saying that
Yes, exactly. So it's like in space, I'll have a point like monopole, and then there'll be a junction of strings. I'll have n of them. Yes. Yes. Sorry. This is n equals 3. Yeah. Well, the charges have to add up to n.
because the monopole has to be
Yes. Yeah, exactly. Exactly. Right. So, as exactly. That's right. Yes. Yeah. Right. So in this theory, there are these objects, the junctions, and I will argue that actually these play an extremely important role in actually understanding the phases of this theory. Okay. What we're going to do is we're going to change the formulation a little bit. We're going to pass to something called the Villon form, which is more convenient for an analytical study because it's quadratic. What it involves is an additional field, n, associated with plaquettes, and you're supposed to sum over all integer values of m. This is meant to, you can motivate this as agreeing with the Wilson form in the weak coupling regime, but by universality, we expect it to have the same phases. It's equally good. It's an equally good model to study in its own right. But the advantage of this Villon formulation is that it makes monopoles manifest. What you can do is you can take these m's, view them as dynamical degrees of freedom in their own right, and consider the sum of the m's over the faces of a cube, and this is describing a monopole. When this sum is non-zero, this is describing a monopole inside that cube. So in this formulation, we have both center vortices and magnetic monopoles absolutely manifest, and we can now ask about what roles they're playing in the phases of this theory. It's not the same, but it has the same symmetries. They are expected to have the same phases, but they're not strictly the same. You can argue that they agree at weak coupling, but they're not literally the same theory.
This is the current.
This is the current. Yeah, this is like a magnetic current. MU live on plaquettes. They're summed without any constraint. Yes. They're summed with no constraint. Yes.
You don't like say that we can all add up all the
No. It could be 0, it could be non-zero. Yeah.
In a way, this is measuring the flux.
Exactly.
Through a cube.
This is measuring the flux. Right. If it's non-zero, you say there's a monopole there.
I was wondering whether you have a monopole of
Yes. It can, this sum can be any integer, can take any integer value
It says monopole
of arbitrary units. Yes. Okay. So what we're going to want to do is we want to isolate the effect of center vortices from that of monopoles. We can actually do this in a very simple way in this Villan model by introducing what is called the modified Villan model. What we do is we introduce a Lagrange multiplier. This is a very standard trick in abelian lattice gauge theory, field theory in general, abelian theories in general. You have a real valued Lagrange multiplier. You introduce this term such that integrating out the Lagrange multiplier field B leads to the constraint that the magnetic current exactly vanishes. So this modified theory is a theory in which all monopoles are utterly eliminated, leaving only center vortices. So monopoles are gone. Now what we can do is we can crank up the coupling, and that ensures that center vortices are definitely proliferating. And we can ask, what is the phase of this theory? It only requires that this particular sum is 0. Yes. So we can actually answer this question immediately because you can exactly dualize the modified Villan action by Poisson resumming the magnetic fluxes. And that gives you this action. So the original gauge field A stays there. So does the Lagrange multiplier B. M's are gone. They've been traded for a new discrete integer variable n. The point, however, is that this is precisely the Villan action of an abelian gauge field, a U1 gauge field coupled to monopoles of strength n. Because essentially this n is now playing the role of these magnetic flux variables in this dual formulation. The fact that there's strength n has to do with this last term, but it's not so important. What is important is the fact that this is an abelian gauge field coupled to monopoles. And when we were sending the original gauge coupling to infinity, this corresponds to the weak coupling limit of this dual theory. So we have an abelian gauge theory coupled only to monopoles in the weak coupling limit. This is absolutely a Coulomb phase. It's a U1 because this B, the Lagrange multiplier field, is now in this dual presentation, the fundamental gauge field, if you wish. And so it's a continuous. Yes, so B is actually compact. Yeah, it's a U1. Yes. 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 It's compact, right. Exactly. Yes. Yes. Yes, that's because, yes, so that's because, so this is not so important for the conclusion, but follows from the fact that in this term, the original gauge field A is quantized in units of 2 pi over n. So it's not really a Lagrange multiplier that sets the dual magnetic current to 0, but it quantizes the dual magnetic current in units of n.
A will you sum over
And n mu nu is, sorry, n? Oh, A. A is summed over integer 2 pi over n multiples of 2 pi over n. Yes. Yes, but it places a mild constraint on the sum of over these dual magnetic fluxes. Okay, so that was the situation in which monopoles were utterly eliminated. What happens when we put them back in? So we can, of course, now just suppress them with a bare mass term. So there's no more Lagrange multiplier. But if you think in terms of dualizing this action, I haven't written explicitly, but if you just, at a qualitative level, you can dualize it explicitly, but just at the qualitative level, what this means after dualization is that you have, again, a dual abelian gauge theory of a U1 gauge field, which is coupled to monopoles as before, but now coupled to heavy electric charges. The monopoles which you have reintroduced become dualized to electric charges, and they're heavy. Okay? Because these dual electric charges are heavy, you cannot change the fact that you're going to get a Coulomb phase at sufficiently large mass, as well as sufficiently large coupling, the original coupling. This is what I'm just adding. This is a deformation of the. Yes. Yes. That's right. That's right. This is a deformation of the Velan. So I add this. This is a deformation of the Velan, and it just is controlling the sum of the monopoles. So I want.
So you would expect that in when the mu naught is very large, there is all these MUs to be.
Yes, exactly.
Because you're putting large cost for.
Yeah, exactly. Yeah.
In the previous one.
In the previous one, they were just completely absent. But I want to argue that it actually persists when you have a finite but sufficiently large monopole mass. Yeah. And I want to emphasize this is all while center vortices are proliferating. That is essential. So this is the phase diagram. On the right here, this is n greater than or equal to 5. You simply get, you can access the Coulomb phase without actually turning on a monopole mass. But if you want to see it for n equals 2, 3, and 4, you have to turn on a monopole mass, but it's there, and it's a generic phase. It opens up as soon as you turn on a sufficiently large mu. Oh, the 5. To be honest, I don't know of a good reason why 5 is the special number. I think it's just kind of a non-universal fact. Sorry? Yes. These are the results of numerics. All I can say is that a Coulomb phase is generic, that it exists. So numerically, this was known for n greater than or equal to 5. There was no explanation. But in fact, it's true for any n. And the underlying reason is this interplay between vortices and monopoles. Vortices have to proliferate, but monopoles have to be suppressed. And that's the underlying reason why the Coulomb phase is emergent. That's the most I can say, but I can't tell you where exactly these phase boundaries are. Sorry, beta is 1 over e squared. Yes, yes. Sorry about that.
Some kind of long distance effect.
Well, this is the confined phase is gap. So I would say it's an empty theory in the infrared limit. The BF phase is described by, well, I'll talk about it in a moment. It's described by a BF theory. And the Coulomb phase may have a bunch of stuff, but I will attempt to give a sort of Landau-Ginzburg type of analysis for this. So far I've been concentrating on a particular model for the sake of concreteness. But I'll move on to this Landau-Ginzburg type of description. Okay. I just wanted to point out that these predictions about the existence of a Coulomb phase in Zn lattice gauge theory for small n smaller than 5 was studied numerically recently, and the existence of this Coulomb phase has been confirmed. So I'll explain this picture in some detail. So what is shown here is a ratio of some correlation function. And the dashed line is the result of having an algebraic decay of characteristic of the Coulomb phase. And you see here the results of numerics for various values of n for the same correlation functions, Z3, Z4, and Z7. Z7 is indicated simply because this is a case where the existence of the Coulomb phase is definitely established. Small n is lattice units. So it's distance in lattice units. Yes. Yes, I mean long distance, yes. Yes. So you see that all of these have an excellent agreement with the theoretical value predicted by a Coulomb phase. These circles are actually also quite interesting. What these are indicating are smeared Polyakov loops. So what you do is you take a Polyakov loop and you sum over all, spatial sites, and that gives you a complex number, and you plot that here in the plane, and for a given configuration. And you see here that in the Coulomb phase, as you sample all these configurations, you actually fill out this circle. A, yes, of the original description. In here. This, yes. So this is the complex plane. It's the value of the Polyakov loop. The holonomy, yes. The summed over all spatial sites. So we call it the smeared Polyakov loop. And for each configuration, you just plot a point of the smeared Polyakov loop. And what this is showing is that as you sample many configurations, these values fill out a continuous circle, which is characteristic of a Coulomb phase. There's no gap, right? If it were, say, exactly, right? Exactly. If it were a Higgs phase, you would see these gaps. You mean these labels? Yeah, these labels are just the actual deformation parameters. So in Z7, there's only one parameter that these authors worked with. They only worked with one coupling. And again, that's because for n greater than or equal to 5, it wasn't necessary to introduce another coupling to find the Coulomb phase. So you just find it tuning one coupling. For Z4, rather than turn on a monopole mass, what these authors did was they turned on some different, larger plaquette action. So a larger Wilson loop in the action. They did that just because I think just based on the principle that this should be a generic phase, you should be able to find it with. Why are they not in the unit circle? Yes. It's an average. But it's an average, yes. So yeah, that's right. Yeah. So the Polyakov loop on a spatial site, right? It's like. You have something like this. This is a loop which passes through the spatial site X, say. This is on a unit circle, but then what you're doing is you're summing over all spatial sites over some volume of the lattice.
Receiving the Z3 one, not quite the ones.
You mean is it perfectly a circle? It doesn't look perfectly a circle. Yeah.
It looks like it has 3 poles.
Right. That's true. I guess I would say that this is a qualitative indication of the emergence of the photon phase, but really I believe what's definitive is the correlation functions.
Yeah, I guess even these things take values not just on the unit circle, but
yes.
groups of units. Right?
Yes.
So,
yes.
So I guess that remnant of that is still there.
Mm-hmm. Yeah.
So it's maybe just that symmetry.
Yeah. Yeah.
If that 7 becomes probably.
Mm-hmm. Yeah. Yeah. Okay. So I'd just like to pause here and just note what has happened. So we've found that center vortex proliferation is a necessary but insufficient condition for causing confinement. This was, this is basically very cleanly established in the context of this model, but I believe it's perfectly relevant for the situation in non-abelian lattice gauge theory as a matter of principle.
Why do you say necessary? I mean, at least from what you said.
It's necessary because what I'll argue is that confinement will occur when both vortices and monopoles.
So far, you showed it's insufficient.
So far, I've showed that it's insufficient. Yes. Okay. You're right. Yes, I've showed that it's insufficient. Well, okay. I should say, I mean, I'm sort of accepting the fact that monopoles, when monopoles proliferate or condense, that is what causes confinement. I mean, I suppose to some extent, this is kind of a rigorous statement if you can define monopoles, right? But monopoles are attached to the junctions of vortices, right? So if monopoles proliferate, then vortices have to proliferate as well because they're attached to them. Will automatically proliferate. Exactly. Exactly. Yes. Yes.
You expect these statements to be true beyond the Zn.
I expect this to be true beyond Zn. Yes, absolutely. Well, yes. I mean, what is not true is this idea. Yeah. I mean, this idea that this that center vortex proliferation, because when they proliferate, they produce this oscillating phase factor when you compute the Wilson loop average. That is an incorrect mechanism. That cannot be the case. It's not, because it's not the case. That is an incomplete mechanism. The only place it's true is in 2 dimensions. In the Coulomb phase, they do have an expectation value, but they have a
this argument that you were saying.
yes.
Okay, so technically, Wilson loop has an expectation.
Yes. 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 No, so that's false. That's the thing that's false. Yes. So in other words, another way of putting it is this analogy with symmetry restoration for an ordinary symmetry, restoration via domain wall proliferation. That's correct for ordinary symmetries. It's incorrect for this one form symmetry.
Yeah, I'm just trying to understand. So what is wrong about the argument?
Yes.
In,
oh, I see. Why is that? Why is that?
We kind of disorder the Wilson loop average, but you're saying we didn't disorder it enough.
Yeah. I mean that must be what's happening according to this argument. Yeah. But I'll explain, I mean, why this intuition, why this analogy with domain walls, why that's not correct here. Yeah. Okay. So this is now the second part of the talk, which will be more qualitative, but I want to present a more general perspective on this question. And I want to ask the question, what are the generic phases of a theory with only this center symmetry, or ZN one-form symmetry in this modern parlance? What we'll do is we'll consider the deformation class. And this is a term which is coined by Seiberg. The idea is that you're not dealing just with one theory, but you're allowing couplings to arbitrary degrees of freedom at short distances, such that you're not changing the low energy physics, or you can make various perturbations. This is an idea which is inspired by the way that condensed matter physicists do quantum field theory. This is how to phrase it in a continuum language. So this is known as the deformation class. And so we're going to ask, what are the generic phases of the deformation class of a theory whose only symmetry is this center symmetry, ZN one form? It's not. So deformation class constitutes more than phases, right? So you can have various phases in a deformation class. This is, by the way, so this is the picture which is generally shown. So you can kind of start with one theory, you make some perturbation, and then it goes to some other theory, right? But then you can couple to some degrees of freedom at short distances that takes you up, right? It's such a way that you're not changing low energy physics, so that takes you up, and then you can make another relevant perturbation that takes you somewhere else. So this all like anywhere you can get via these kinds of steps constitutes the deformation class. So it's a rather large space of theories. So this means, that you're coupling to different arbitrary degrees of freedom in such a way that you're not changing low energy physics. So if you actually go, so RG flow, you should think of as going down. So what that means is that because you're coupling to degrees of freedom at short distances such that you're not changing low energy physics, if you go back down, that takes you just to where you started. Changing the low energy phase. Yes, that is, yes. So it's not all theories that flow down to the same place. It's because of this operation that you may get to a different place. Okay, but this step means you're looking at all theories that flow down to the same place. That's correct. Yes. Yes.
Let's say I have an electric line.
Okay.
So paramagnet is system information class, paramagnet class, or
No, these are, yeah, I mean, these differ by tuning parameters of the same system, so that's the same definition.
so the full phase diagram is both paramagnet, ferromagnet. This is a different.
It's a subset. So this is broader than, right? So this is broader than just tuning parameters in a theory.
Because I would say going to paramagnet plus paramagnet is low energy.
That is changing low energy physics.
But
No, so there's two.
Part of the same thing.
No, sorry. There's two distinct operations. One is where you couple to short distance degrees of freedom such that you don't change the low energy physics. The other is by varying parameters, and that will change the low energy physics. So there are two kinds of operations you're allowed to do, and any combination of these two operations will fill out the deformation class. That's the idea. So you will absolutely explore many different phases when you're filling out this deformation class.
So the deformation class of the thing, includes all solid states. They all experimentally observed.
Presumably, yes. Yeah. I mean, yeah. So I will construct. Yes, yeah. So I will devote the rest of the talk to the example. Yes.
You were constructing them.
Yes.
There the vortices are monopoles.
So yes, I could discuss yes. So the phases are different in 3 dimensions. Yes, but I would say that the vortices are always different from monopoles. So I will always interpret a vortex to be something which has a codimension 2 world volume. A monopole will always have codimension 3 world volume.
You don't have vortices in this sense. Or they would be what you call domain.
Yeah. So well, in 2, you mean 2 plus 1 or?
2 plus 1.
Yeah. So in 2 plus 1, the vortices would be particles.
Yeah. Well, I mean, monopoles are also particles.
Well, I would say, yeah.
Okay, I don't know.
Yes.
Yes.
Those are
what you're calling.
Those are what I'm calling monopoles. Yes. So by monopole, I always mean the thing which has a quantized magnetic flux of some yay integrated over a 2 cycle.
Because there was this Coulomb picture of confinement.
Yes. Yes.
Which is supposed to arise from a proliferation
of monopoles. Yes. Yes. I'll discuss. Yeah. I'll touch on that shortly. So. Okay. So we want to consider the deformation class of theories with this symmetry, Zn1 form only. And we're going to make the following assumption. We're going to make the assumption that in this deformation class is a phase in which the center symmetry is spontaneously broken. If that is the case, then the low energy limit is described by this topological theory, so-called BF theory. And I've written it in general dimensionality D, capital D, the space-time dimension, because I want to illustrate how this argument works in various dimensions. I'll discuss 2, 3, and 4 dimensions. Sorry, so this is my, so I'm just doing this to indicating the degree of the differential. Yes. So essentially, the full content of this theory is contained in this correlation function. If you take a Wilson loop of A, and then you also take a Wilson volume of B, you compute the correlation function, you simply get a Z-n phase factor, the phase being given by the linking number of these two manifolds, C and V. This is the full content, essentially, of this theory. This theory also has, what are the symmetries? Well, it's got the Zn1 form symmetry, of course. This is given by discrete shifts of A, technically shifts of A by a flat connection with Zn holonomy. But there's also a symmetry, a similar symmetry given by shifts of B, because A and B essentially enter quite symmetrically in this action. The same exact symmetry. It's also a Zn symmetry, but this is not a symmetry that we have assumed of the original theory. So in other words, it's an emergent symmetry. So whenever we have an emergent symmetry in some low energy effective description, we should ask, is it robust? Does it deserve to emerge? And what that means practically is that we should break it and see what happens. So how can we break this symmetry? Well, generically, the way that we understand how to break such a symmetry is to couple the theory to excitations that carry gauge charge that couples to B. Now, such objects necessarily have world volumes of codimension 2, and they introduce this factor into the path integral. And because of this correlation function of the BF theory, giving this phase factor, we very naturally interpret these excitations as center vortices. You see, just the consideration of breaking an emergent symmetry, you see that you have to have heavy center vortices in the picture. Well, of course, that's perfectly natural, because that's, in some sense, the very meaning of spontaneously breaking. Or if you like, I mean, one always expects such heavy excitations to be there when you spontaneously break such a discrete symmetry. So it only really emerges in the limit in which you completely decouple these codimension 2 excitations. Okay. So by coupling to vortices, have we got back to the symmetry of interest? In fact, we have not, because by coupling to vortices, we have introduced a new symmetry. What is this symmetry? This will, in order to explain what the symmetry is, we'll have to consider a monopole configuration of A. So we consider a monopole configuration of A. Let's say the monopole world volume is M. And let's consider the change in the BF action under a gauge transformation. The BF action changes like this. It's not invariant in the presence of a monopole. And what this is showing is that a monopole has gauge charge that couples to B. What this means is the following. In the BF theory alone, there's no gauge invariant notion of a monopole because it's not gauge invariant. However, once you've introduced the vortices, you can have a gauge invariant definition of a monopole because you put the monopole world volume on the junction of open center vortex world volumes. That gives you a gauge invariant configuration. And since you have a gauge invariant notion of a monopole, you then have a conservation of magnetic flux, and this applies a U1 symmetry. You see, introducing vortices, it broke a symmetry we didn't want, that was emergent explicitly, but it gave us a new one. We have to break this new one. And we can do that by introducing these monopoles as dynamical objects. Yes.
What exactly like this? Is that the center vortex or this A?
This A.
That is what we are doing.
No, no. So the center vortex, I would say, is the thing.
But this you introduce in the.
So it introduces factors into the path integral. So you're kind of summing over all possible world volumes, and each world volume is accompanied by this such a factor, as well as additional weights. I mean, also has to have some tension. You're saying, yeah. So V is the center vortex world volume.
One center.
For one center vortex, you have one such factor. Yes, but for many, you have many such factors, along with accompanying weights. Yes. In this slide.
Yeah.
Yes. So the monopole of A, indeed, the monopole of A, the point is that it carries gauge charge coupled to B, right? But so do the center vortices, right? So you can compensate the fact that the monopole has gauge charge by attaching it to center vortices. That gives you something gauge neutral, hence you have a gauge invariant notion of monopole.
So there is the original symmetry beta with the beta.
Yes.
That you have broken.
That we have broken, exactly, by coupling to center
This
vortices.
B plus B omega.
This is simply a gauge transformation. So B plus beta is a global symmetry, but B plus D omega is a gauge symmetry.
Symmetry of the origin.
Yes. Yes, exactly. Okay. So what we've done, just to summarize, is that we have started with the BF theory. This had an unwanted symmetry. We wanted to break this unwanted symmetry intrinsically. We did this by introducing vortices. But in doing so, we produced another unwanted symmetry, and we broke that intrinsically by introducing monopoles. So now we have a system. So you see that vortices and monopoles arise naturally when we ask a question about the deformation class. This is just the same picture as before, indicating that monopoles are lying at the junction of vortices. Okay, so now I want to discuss the application of this framework to understand the phases of various in various dimensions. I'll discuss d equals 2, 3, and 4. So we'll start with d equals 2, which is rather simple. In this case, vortices are instantons, and monopoles just don't exist. So we want to break this unwanted Zn symmetry associated with shifts of B. B was a d minus 2 form, so it's just simply a scalar. And we can do this by simply adding this perturbation. This is a perturbation we can add that will break this shift symmetry of B. The point, however, is that this perturbation is relevant. It's relevant in a rather trivial sense because the BF theory is topological. And therefore, I mean, these local operators basically have trivial scaling dimensions. They're just always relevant. And this immediately gives you a confining theory. And you can do this by an explicit computation of the Wilson loop of A. The calculation is basically the same calculation that might be familiar if you've ever studied the two-dimensional Abelian-Higgs model in the Higgs phase. The confinement due to vortex instantons, it's the same calculation essentially. And so we see that the only generic phase is the confined phase. So this explains in very general terms why confinement is so generic. You essentially can't get it unless there is some symmetry reason or anomaly reason that this perturbation is forbidden. If the symmetry is only the Zn center symmetry, then you always expect such a perturbation, and hence you always expect it. So that's the conclusion in d equals 2. Are there any questions about the equals 2?
There's no way to create conforms.
Yes, or at least it's not generic. You would have to forbid such perturbations, but there's no symmetry reason. I mean, you can only forbid them if there's a symmetry reason or anomaly. But if all you have is the ZN1 center symmetry, then you generically expect such perturbations. That will restore the ZN1 symmetry. There are, of course, models where, you have a deconfining theory in 2 dimensions, but it always involves some other symmetry or some mixed. Now in D equals 3, vortices are particles and monopoles are instantons. And now this is the way you can get a deformed Lagrangian. The first term is just the BF term we started with. The second term denotes the coupling to vortices. Vortices are associated with the scalar field phi here, and it carries unit gauge charge coupled to B. Introducing monopoles, this means adding monopole operators to the action. And the fact that you have to multiply the naive monopole operator by the nth power of phi is a reflection of the fact that the monopole operator of A carries gauge charge, n units of gauge charge, and you can compensate it by dressing it with the vortex. I've also added just various other terms. These are generically there. Kinetic terms for A, kinetic terms for B, as well as a potential phi. And now we can ask, what are the phases of this theory? We'll suppose phi is heavy, and we can integrate it out. Then we would simply drop all occurrences of phi, and we would get back to the BF phase. And so this is the Higgs phase. So that's a generic phase, a Higgs phase. Now suppose phi, the vortices, condense. If phi condenses, then B gets a mass, and we can delete all occurrences of B. And what we're left with is essentially just a gauge theory of A perturbed by monopole operators. And this is precisely what Polyakov studied in his celebrated pioneering work on confinement. This is Polyakov's mechanism. And so this is a confined phase. Note the absence of a Coulomb phase. This is because the monopoles are always relevant. Finally, we come to D equals 4. And here I'll just be qualitative. Vortices are strings, and monopoles are particles. And now we can ask, what are the phases? Now, if the vortices and monopoles are heavy, all these deformations go away, and you go back to the BF theory. So that's the Higgs phase again. On the other hand, vortices and monopoles proliferating, this is, of course, the confined phase. And now what happens when vortices proliferate, but monopoles are heavy? What happens in this case? Well, in this case, if monopoles are heavy, then you get a conservation of magnetic flux, and hence you have a U1 symmetry which emerges associated with this conservation law. On the other hand, the center symmetry that you started with enhances to U1. And that's because vortices proliferating, Higgs is B, and Higgsing B by a generalization of the Higgs mechanism, essentially is what it kills the BF term, and that's what allows this enhancement of the center symmetry acting on A to a full U1. So now we have 2 U1 symmetries, electric U1 associated with A, and a magnetic U1, which emerge because monopoles are heavy. And these actually always have a mixed anomaly. And the only way to satisfy this anomaly is by the emergence of massless photons. This mixed anomaly means what? It means that either one of the symmetries is spontaneously broken, or you have some conformal theory in the infrared limit. But in either case, you have a photon in the spectrum. The one we started with, yes. Exactly. Yes, exactly. Yeah. Exactly. Exactly. In the Zn lattice gauge theory example. Exactly. Exactly. Yes. And actually, from the point of view of symmetry, you can also understand why this Coulomb phase is natural. Because, I mean, when you completely eliminate monopoles, this is the symmetry reasons, because you gain this U1 magnetic symmetry. Yes, I haven't talked about this mixed anomaly, but in the Zn theory, there is a way to see it. Sorry? Well, that's sorry. So unfortunately, this is a different B. Yes, this is a different B, unfortunately. So this was a dual gauge field. Yeah. Yes. I believe, yeah. So these Vallon actions are quite nice, and I believe it seems to be generically the case that if there's some mixed anomaly in some that you were expecting, it turns out to hold exactly in these Vallon formulations. Yes. Let's see. Yeah, so you have to. Yeah, I believe if you turn on backgrounds for these respective symmetries, you should be able to see.
This continuum.
Yes.
Something like that.
There should be something like that in 40, and there's literature on this. I expect there are people that here that understand this a lot better than I do. But yes, I mean, there's some literature about coupling to higher dimensional objects, brains, and so on. This higher dimensional generalization of the Higgs mechanism, what happens with Higgs, or when you condense strings. So this, yeah, there's a literature. But I just wanted to be qualitative. It's only in, yeah, so admittedly in D equals 2 and 3, we stay in the realm of ordinary quantum field theory. That's true.
Description itself is
Yes, so that's true. By the way, so this was just my, actually, this was my last slide. So I'm happy to take questions at this point. Yeah, I mean, n greater than or equal to 5. I mean, all I can say is that for n sufficiently large, of course, Zn is starting to look like U1. That's not really a great argument, but it's reasonable. N is, Zn is starting to look like U1. Why n equals 5? I mean, I really can't say. I think it's just a fact of life. Yes, yes, yes. Mm-hmm.
guess the problem here is we have this point.
Yeah, I mean, I think the only way I know how to talk about breaking the symmetry is by coupling to extended objects. The field theory level, yeah.
Are there any question here offline? Are there any question online? I don't think so. So, okay, so let's thank the speaker.
Thank you very much.
Thank you.
Yeah, no, thank you for having me. Yes.
The last,
Yes. Yeah,
last week.
yeah, it was last week.